Hello all, this is our second lecture on space-time block code. Here, capital X given matrix is an OSTBC since it follows the x into x Hermitian proportional to I. Whereas it also follows the amicable orthogonal design as we have discussed in our previous lecture. The rate achieved through this particular design is 1, which is the full, and diversity is also equals to 2, which is the maximum diversity we will get across the two transmit antennas, right? So this is famously known as the Alamoti STBC. Alamoti is the name of the uh, designer of this code. In this lecture, basically, we will learn how this particular matrix is going to be transmitted through a 2 cross 1 system. Here, in the first instance of time, this first column will be transmitted uh, from where first transmitter transmits x1, second transmitter transmit x2. Similarly, in the second time of instance, second column will be transmitted from where the first element of the second column minus x2 conjugate will be transmitted through the transmitter 1 and x1 conjugate through transmitter 2. So in a mathematical form, we can represent y1, which 1 represents the instant. This 1 represents the instant, right? H1, H2 are the two channels, wireless channels from the transmitter 1 to receiver and from the transmitter 2 to the receiver, right? X1 and X2 is the first column, this first column, right? And this N1, or here we are adopting it as E1. Please rectify all these typing mistakes in the notes, so I will going to post on the WhatsApp group. So similarly, in the second time of instant, y2, h1 and h2 are the same channels. We are assuming that for this O block, the channel will remain constant. The h1 for this and h1 for this will be same. It means h1 remains static for these two time intervals. Here we assume it like that, right? So h1 h2 minus of x2 conjugate second column and x1 conjugate plus e2 second time instant, right? So now onwards, our motive is to form this equation 2 like this: x1 and x2. We want to make this minus of x2 conjugate and x1 conjugate in the form of x1 and x2. So what we can do for that? First of all, we need to remove the conjugate. So we need to conjugate from left hand side and the right hand side of this equation, right? So we will achieve y conjugate to h1 conjugate h2 conjugate minus of x2 and x1, right? Now we need the shuffle this x1 upward and x2 downward. Similarly, this h1 and h2 will going to be shuffle. Overall equation needs to be same, right? So in a similar way, this minus should not be there. This is again one more typing error. Please correct it in the notes. So as we shuffle it, x1 up, this x2 is here and x1 there. So we just prepare minus. Instead of minus of x2, we put minus with h1. It will doesn't make any change in our equation when we open it in this matrix, right? Now we need to shuffle this. So as we shuffle it, x1 upward and x2 downward, this h1 and h2 will also shuffle left to right, right to left, vice versa, right? So our another equation, this is known as b, right? And this will be my A equation, let's say. This is our A equation, right? So this is this equation A and this equation B. So if we stack these two equations, what we will get at the left hand side, y1, y1, y2 conjugate, y2 conjugate. Similarly, h1, h2, first row, h1, h2, second row, h2 conjugate minus of h1 conjugate. And x1 and x2 is common here, x1, x2 and x2, x1 and x2, right? Plus e1, E is nothing but additive white Gaussian noise, right? And e2 conjugate, right? So what we are getting here, this H matrix is known as effective channel matrix, which is of dimension 2 cross 2. It means our meso 2 cross 1 meso system is virtually converted into an 2 cross 2 memo system, right? In a matrix form, we can represent this in a vector or form. In another form, you can say that we can represent it like this, where this y. So generally, we denote the vector with a small letter having a dash underneath it, and this is for vector, right? And capital thing like this H is a matrix. So is a matrix here. So we can do one thing here. We can put a bar here, here, and here as well. These are vectors and this is a matrix. So the interesting observation is this: H into H Hermitian is an orthogonal, which yields mod norm square of H I2. I2 is an identity matrix, right? This is your H matrix. This is your H matrix. So if you do this operation of H into H Hermitian here, you will get norm square of H into I2. I hope all of you remember what is this norm square, right? This is your norm square. Norm square, right? Whereas norm of H is nothing but under root of mod of H1 square and mod of H2 square. Mod of H2 square, right? So now we want to evaluate the SNR of this first channel and SNR of this second channel, right? Or I can say that we want to know the input output relation, overall input output relation, or overall SNR of this particular system by employing this Alamotti STBC, right? So what we can do here, we can do a beam forming here since it's a 2 cross 1 system. However, we are employing Alamotti STBC or orthogonal STBC because of the absence of the channel state information at the transmitter, right? However, receiver always have the knowledge of the channel coefficients, so we will use receiver beam forming. Receive, we put the beamforming weights at the received signals, right, which is quite intuitive and which is quite practical to do. So the beamforming weights w1 is function of h1 and h2, given in this form: h1 divided by norm of h, h2 conjugate divided by norm of h. If we can observe, it's nothing, it's the first column of our effective channel matrix H, right? If we common out norm of h, it will become this. As I told you, norm of h is nothing but under root mod 1 mod of h1 square plus mod of h2 square, like that. Similarly, W2 is this second column of the effective channel matrix H. Right? Right. This already explained to you what is the difference between the transmit beamforming and the receive beamforming. You can go through this theoretical material and let me know if you have any issue with that. So, y is the received vector. So we will put a first beamforming weight W1 Hermitian, multiply it with the received y vector, right? So by substituting the y vector here and the value of W1 Hermitian, W1 Hermitian is this H1 H2 conjugate 1 divided by norm of H, right? We put it here. This W1 Hermitian is also going to be multiplied with the noise term. So after this manipulation, we will find out that by multiplying the W1H, we will get our input output relation of the first channel, or you can say that the first symbol X1, right? So similarly, I can put it here as SNR1, which represents the SNR for X1, or the you consider for the first branch, or you can say that like this, right? So what will be the SNR of this? Norm is here, so norm square divided by the variance of this noise, which is normalized and doing the after manipulations, sigma n square expectation of E of x1 mod square. E of x1 mod square is nothing but the p1, right? So this is our first SNR, or representing p1 r x1. Similarly, for x2, multiply w2 Hermitian with the y vector and substituting the corresponding values, we will get the SNR. This is our second SNR in terms of p2, norm of h square divided by sigma n square into p2, right? Where p1 and p2 are the power distributed corresponding to the symbol x1 and symbol x2 respectively. However, p1 plus p2 is equals to our total power p or pt, which is a fixed quantity. So what would be the best optimum solution for the devoting the power across the transmitter 1 and the transmitter 2? It's obvious that P1 should be P by 2 and P2 is also P by 2. Hence, this will also going to be satisfied. Therefore, the overall SNR of the system in terms of P, which is gamma equals to P by 2 mod of h square divided by sigma n square equals to this, and it leads to final this answer. So this is our OSTBC SNR. It is quite similar to our transmit beam forming SNR. When we have the channel state information at the transmitter, or we called it as a beam forming SNR, which is look like this: mod of h1 square plus mod of h2 square into gamma bar, right? So this 1 by 2 is the factor which is making the difference between the OSTBC SNR and the beam forming SNR. So SNR of Alamoti STBC is half of the SNR of transmit beam forming, means when the CSI is available, right? CSIT is available. So if you convert this 2 into dB, you will get that 3 dB, right? So it's a 3 dB loss in the Alamoti STBC. However, the diversity would be the same, that would be 2 mod of h1 square plus mod of h2 square. Whereas there will be a 2 dB, 3 dB of loss recurred by the Alamoti STBC. Or you can say that if we don't have the chance state information at the transmitter, and we want to attain the full diversity, we will employ Alamoti STBC, and it will cost us 3 dB. However, provide the full diversity which is equivalent to the transmit beamforming.